This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Most probably will go through this one.
Yes.
But then your IC, your connection will be something like this. That's what I'm trying. So your analog is coming. So this is the part we are talking. From here only we are connecting to IC1.
Yes.
IC2,
Yes.
and then this is the ground.
Yes.
And then when you have some, here we will be connecting bypass.
Yes. The bypass is 0.1.
Yeah, bypass is
million,
small
right?
because we don't have much space, so we will be connecting only the required values. So when you have switching, what will happen is then here all the noises will be shorted through this one.
But why not this one? But this one, the impedance is much more
But then
smaller.
it has to come, this will come here, the noise will come this point.
Yes.
First it will come to this point,
Yes.
and then see whether this is low impedance or this low impedance.
So
Yeah,
it's
yeah.
a distance.
Yeah.
It's a
Because
distance
distance,
problem.
yeah. Which one is the shortest? That will take the shortest path.
Okay.
And then if it is the shortest is there, it will go through like that.
Okay.
It's like, if you got a short here, the current will not come here. It will just short to the ground.
Oh.
Yeah, but still something is coming. That's the reason we are putting like here.
Because I think that this one, the impedance is much more smaller.
Yeah. So then I'm drawing this one. So I will be talking maybe the PPT song. Yeah.
But if we add an inductance here, it will also preserve it, like stop at the current change.
Yeah. But that's the noise we are stopping from here.
Yeah, but we also like switch, probably, for example, transistor here.
No, transistor. But then that circuit is closed here. You don't need this. We are not drawing from here. That's the reason we put this one here.
So this is also decoupling.
Yeah. See, it's a tantalum. Yeah, that's what I'm going to explain now. Yep.
So I will ask for this one. When it's high frequency, where does noise come from? If we assume this is a very constant DC.
So the noise means when this is on,
Yeah.
then your collector current will be coming.
Yeah.
It is drawing maybe 20 milliamps.
Okay.
And then from the power supply all the way it is drawing 20 milliamps. When it is off, this is off.
Okay.
So then your current is switching here.
Yeah.
So drawing current, not drawing current, depending upon the signal.
Yes.
Then that is creating the supply here. Because from the supply you are creating a lot of current, switching noises. The current is drawing, not drawing, drawing, that type noises.
Okay.
Yeah. So anyway, I'm going to discuss this more because the time is up.
Okay. Sure.
Thank you. Okay, so we will start from here. So this is a very good design. Why? Because here you have got the voltage regulator might be generating say plus 5 volt, and then you have got a decoupling capacitor, then you have got a ferrite bead, then this is an analog voltage. From here you will be taking all for the analog ICs. From here you will be taking all for the digital ICs. Then the advantage, so what is the advantage? So we can draw it and check it. So when you have this diagram, so this is your voltage regulator. Maybe this is a plus 5 volt and then this is a ground. And then in this design, this will be going to maybe IC1 digital. And then you may have got again bypass and then maybe going to IC2. So please be careful because I am going to ask you a question. So this is IC2. So all these are digital. So I am writing D, so I am circling. So these are the analog, A analog. And then so this design is very good. Why? Because your power supply, this is your power supply or regulator IC. From there you are getting 5 volt. So this will be charging to the 5 volt. And then so this part to here, this is charging to 5 volt, and then this is the source for the entire circuit, both analog and digital. So this from here only it is drawing. See, one line is coming. Then again it is coming. So here you got a ferrite bead. So this will prevent any noises entering from here or any noises coming from here. So this both the point will be isolated. This inductor will be a short for DC. And then these ICs, so I am going to take digital. So this is the digital part. So when the digital is switching, lot of noises, some noise will come, and then if you choose these values properly as per the data sheet, then those noises will be going to the ground, the noises is going to the ground, noises is going to the ground. And then what will happen is maybe a little bit will come, and then that may be shorting through this way, and then remaining will be shorting through this way, and then the circuit will be for this digital circuit, because this is 10 microfarad a big value, then your circuit will be closed here. Current is coming like this, and the digital part is, see. So all the digital circuit will be switched like this. From this local capacitor, it is taking the power, and then it is ground is returning to here. So not from here to ground to here. See, all the switching is happening here. Same with analog. Analog, everything is drawing from this local capacitor, and then it is returning to this ground, something like this. And then any noise which is not bypassed by this one will be shorted by this one or this one. So this is kind of a local cell. It can be like a local cell. And then this ferrite bead will make sure that any noises from this digital line, because mostly from the digital line only noise will go to this side. It will not come, because the digital line, even if some noise is coming, this ferrite bead will stop it here, all the noises. It will not go to here. And the length due to the track, see here we are solving that issue with this one. The circuit is closing here, circuit is closing here, and then even if the voltage regulator is far away, then we will connect another one close to this ferrite bead. If the voltage regulator is close by, then we don't need this one. But it's better to connect one more here if you got space. So I hope this part is clear. So now we isolated. But then the problem is, what is the problem? Here there is a big problem now. Yeah, I think the capacitor we can choose in such a way that it will not affect the charging. I know what you meant. High frequency, that if you can choose the capacitor values correctly, it will not affect the charging. But the problem here is, you have got noise. Now here what you have achieved? Maybe that's my question. So by doing this one, we achieved several things like inductance, track inductance due to switching, the length of the track we avoided, then the noise in the power line we avoided. But then what you are doing is, you got noise in the power line, that is a track, then you are using capacitor and shorting to the ground. So now you got a big monster in the ground plane, because all the noises going to the ground plane, what will you do? You know what I meant? So you got all the noises, see, from the digital you got noises, you are coupling to the ground. And then here also you are coupling to the ground. Obviously digital noise is much more than the analog noise. And digital circuits are more prone to the noise. Why? Because if you got a 200 millivolt even noise, that will not come that much exaggerated value. 200 millivolt, your digital zero is maybe 0.5 volt. That is a zero. It is not even reaching that value. But analog ICs are very prone because of the gain. Amplifier, if you get 200 millivolt, it might sometimes saturate because of the big gain. So then your big monster is now in the ground plane. So all the ground plane here, you got a lot of noises. Here also you got noises. If you connect both the ground planes together, what will happen? You are mixing the noises in the ground plane. Then why we bother about a ground plane? You might think that ground plane, no, we don't have any issues. No, ground plane means the current is going, then the current is returning to the ground plane. So the current is flowing in the opposite direction in the ground plane. So that you should always keep in mind that your ground plane is not a static one. Ground plane means return of the current. So if your noise is there in the analog plane, noise is there in the digital plane, mostly digital noises are bigger. If you are not isolating the ground, then this noise again coupled in the, it is coupled to the ground. If you got a ground noise, definitely it will couple to the amplifier. So that is the reason we will isolate usually. So we have to isolate the plane. So then what we will do is the top plane we have isolated like this. Then the ground plane, so this may be the ground plane. So we will be ground plane, we will be isolating both digital and analog. And then when you are isolating the ground plane, then what you will be doing is, so this is a ground plane, so this is a underneath plane. So that is this is a ground plane for this circuit. And then this is a, I am putting like this, so that it makes sure that this is a top. This is the top layer. So top layer means that is a power supply layer, and then this is the bottom ground. So this is a ground plane. So this is a digital ground, DGND. So this is a bottom plane. So that's the reason I wrote like this. So then here you got a analog plane. See. So this is a analog ground. So again this is the bottom of the PCB. So you got a analog plane. Top layer you got a power supply, and then bottom you got two ground planes. And then when you have two ground planes, you isolated both the ground planes here. So do you have any issues if you isolate the ground plane? So when you are isolating, there is a problem. Then the current is going through, because some of the analog signals, this output may be coming to the digital IC on the top layer. So this is the top layer. You know what I meant? Because when you have analog ICs, when you have digital ICs, you can isolate the switching noise, and then you can put two ground planes. But from analog, you may be going some signal to digital. For example, in your case for DSO, your amplifier or filter output is going to the ADC. So you got ADC output is going to the buffer, digital buffer. So somewhere you have signal crossing. But when the signal crossing, if you isolate the ground, what will happen? Will the current will flow? Because your signal is coming, and then you completely isolate the ground. So where is the return path? You know what I meant? Yeah, so there is no return path. So then what you will do is, the straightforward way to do is, we will connect only one point here, short it. Only one point, that is called a necktie. So that is called necktie. So only one point. Why only one point? Because you can think of as maybe two swimming pools. So close by. In one swimming pool, that is our ground plane. You make lots of noise, lots of big waves. Another swimming pool, that is kind of a static. So if you connect completely, what will happen? All the noises will come to, waves will come to the other one. But if you connect with a small pipe, only one line, then what will happen? The coupling, the noise is less here. But same time your circuit is closed. So that is the reason we use necktie. So then people might think I will use necktie 1 here, necktie 2, necktie 3. That also is not a good idea, because then you have multiple paths for the signal. You are creating a lot of loops. So that also will increase inductance. So that is the reason only one side we need a necktie. Because if you don't have necktie, then you don't have the return path. It's like you got the battery, the top is connected, the return path is not there. So that's the reason we use a necktie. Another elegant way of doing this is, there are some ICs, that ICs can isolate even both power line, signal line and ground plane. Then you don't need to connect a necktie. If you got that type of isolation ICs, but then you won't get isolation ICs for all the applications. If you get one, that is good. Then you don't need to connect it necktie. So then that's the idea of necktie, and then that's how we need a digital plane, analog plane. Then in your case, definitely you should have digital plane, you should have analog plane. But then you also got another problem. What is another problem? You got a USB one. So USB you need another ground, because USB means you are connecting to the computer. And then in your case, actually you got a USB ground, you got analog ground which makes sense, you got analog ICs. You got digital ground because you got digital ICs. Then you got a USB ground, then you also got one more called a power supply ground. So you got 4 ground in your DSO. And then in the DSO, again as we made it a bit complex, because it's easy to put 2 grounds, but then we put 4 grounds. Even when you have 4 grounds, then as I said, you can connect the necktie. You isolate all the grounds, and then on the top what you can do is you can put like ferrite beads, tantalum capacitors, so that you are suppressing the noise. But in the ground you can put necktie. But if I put necktie everywhere, then you will forget about the use of isolation ICs. So that's the reason in DSO design, when you have 4 blocks, in one place we will be using an isolation IC. And then that will, I'll show you. So in the DSO design, So you can see that we have drawn it in a neat way. So this is an analog ground. So here you got all the analog ICs are above that. This is the ground plane. Then you got a digital ground. Then you got a power supply ground. So this is a power supply, and then here you got USB ground. So you got 4 grounds, and then when you have these 4 grounds, you can see here your power supply. From the power supply, you can see plus VCC, VW are going on the top, and then we will be using a lot of filters like inductor, capacitor, all these things to avoid the noise. And then the ground, both the grounds are connected only using a one point called a net tie. See, here we have used a net tie. Again here, from the power supply, you got a regulator here, that is 3.3 volt. You need a digital part, you need a 3.3, and then because this is 5 volt, and then again in the regulator here, this part regulator, 5 volt is converting into 3.3 volt, plus power line is isolated because the regulator got some kind of isolation, and then you also got a filter here. Again, your digital ground and the power ground, this power supply ground is using a net tie. But when it comes to see USB ground, when it comes to USB ground, we are not using a net tie. Why we are not using a net tie? Because when you have 2 grounds, so when you have 2 grounds here, see, you have got ground 1, then you got ground 2, and then you also got, this is the bottom side of the PCB, bottom layer, this is again bottom layer, and then the top layer you got here maybe digital D plus 5 volt, and then here it is analog plus 5 volt. So this is maybe analog ground, this is a digital ground. So then this is a 2 planes. So then what people usually, then the conventional option 1, the option 1 design is you are using the ferrite bead, and then you are using a lot of tantalum capacitors, all these things put together. I call it as a filter. So you are a filter, and then this is a 5 volt is coming, and then using the filter you are tapping power, so that the power supply line is isolated. You know what I meant? The power supply you isolated. Then here you will be using a net tie. So here you can use a net tie only one place, so that is fine. But then option 2 means when you have ground GND1, this is the digital, and then you got analog, and then GND2. So this option 2 means, so option 2 is possible. Then here what is happening is you can use maybe a isolating power supply. So then you can get some isolating power supply. So isolating power supply means you give the 5 volt, then you are getting another 5 volt that you can connect here, and then there is a ground associated with that one here, and then that is for this one. Then here you got another 5 volt you can connect here, and then another ground, and then these 2 ground will be connected internally, isolated, so that you don't need a net tie, because then you got only one IC. That IC can isolate both your power supply and ground. So in advanced designs, people use isolator. If you don't have isolator, you have to use a net tie. So in your design, that's the reason we are using both. See, here you are using a net tie, and then for this USB ground, we are using a RD0505D, an isolator. In the isolator, this one we don't need a net tie, because in the isolator the ground is isolated, not only power supply isolated. See, then if you got this regulator, suppose this regulator got both the power line and ground plane isolated, then you don't need this net tie. You know what I meant? But then unfortunately for this regulator, only the power supply, the line is regulated, the active plane is isolated. And then so that's the reason we are using like this, so that you know that, okay, so from here why we put different planes, so that you know what is the importance of split design. Split design means when you have analog, we have to put analog ground, then you got digital ground, then you have to use a net tie. Then another lesson you have to learn is even you don't need a net tie. If you got a regulator, in that regulator, if the regulator can isolate both the power line and ground plane, you don't need a net tie. But if you don't have that one, only power line is isolated using the power supply, then you need a net tie. Then when you use a net tie, we are just making the signal complete, the signal flow, but through only one point, so that lots of noise is not going through. Then we also got I think I got a figure somewhere. I will show you. I think I don't have, maybe I didn't bring that figure. I will show you. On PCB, I got a PCB. Maybe this is one decoupling, some way of doing the decoupling. But I got a very good photo of your PCB showing the decoupling part. Maybe I will check it. Just a minute. Yeah, maybe this is a very good. Yeah, I got it. So we got some slides. See, so this is a analog ground, and then power ground, power supply ground, and then USB ground. So USB VCC 5 volt USB ground, because here you don't need a net tie, because this one gives isolation for both the power line, the active plane, and ground. But then here, this regulator, you don't have the isolation for the ground. So that's the reason we isolate both the grounds and use a net tie. And analog, because from here you are getting +5, -5, 0, and then you are using the filter, inductor, capacitor, the filter I discussed. And then so you have 4 planes in your DSO. This is how you have to connect it. And then if you design, look at the design. See, this is a design. So you can see this is an example. So you can see, so this is a digital ground. So you can see digital ICs are so many, so that is the reason this plane is big. This is analog. And then this is a net tie. So this is the power supply ground. See, USB ground and power supply ground, we don't have any net tie, but the ground is isolated, but then you don't have any net tie because you got a regulator IC that is isolating. Then your power supply ground is connected to the digital ground using a net tie. See, this is a net tie, only one connection. Again, power supply ground is connecting to the analog ground using a net tie. Then I can show you the other drawing so that you can see. Here you can see what you can see is first I will take digital ground. So digital ground and power supply ground connected using a net tie. Digital ground, power supply ground. So there is no connection between here analog ground and digital ground because we got a power supply. So we are connecting to the power supply. So power supply ground is connected to the digital ground. So the ground is completed. See, this ground is connecting here, this ground is connecting here. So even if some signal is going here, the return path will be like this. So digital ground is connecting to the power supply ground using a net tie. So that's what you see here. So digital ground is connecting to the power supply ground using a net tie. Again, power supply ground is connecting to the analog ground using a net tie. So that's what the next one. See, analog ground is connecting to the power supply ground using a net tie. Then power supply ground and USB ground. Here you don't need a net tie because this provides the isolation for the ground as well. So that is the reason you don't find you don't find any net tie here. This should be fully isolated. Then, but because you got that RD 05, that IC that provided the isolation. So that is the reason. And then if you don't provide the isolation, if you don't have that isolator, what will you do? Yeah, you have to use another regulator and then to use a net tie. So net tie also is a very good concept, and you can avoid the noise spreading across. So that's how you should be designing the DSO. And I have shown this one so that you know how to design the planes. And then now you know why we need the planes. So then we will be continuing the supply decoupling, but because we used the document camera and explained, now we can go through quickly. Supply decoupling. Load that draws fluctuating current produces voltage noise on the supply and ground power distribution due to track or lead resistance bar inductance. So that's what we said. Load is your IC. When you have IC, when it is switching, it can create a lot of noises. And then this is I have shown. So this is your regulator IC, and then this is your copper track. In the copper track, because of the parasitic, when it is operating at high frequency, means switching. When it is switching at very high frequencies, then it will see the copper track will have parasitic resistance, parasitic inductance. So this will not be causing any problem in low frequency, but in high frequencies this will create. Keep AC off the supply lines by using a decoupling capacitor. See, that's what it says. So we will be grounding all the noises from the supply. So local decoupling. So this also we already read it. It is a good practice to have decoupling capacitors for each IC bar module on the board. Each decoupling capacitors for those. So these are not ICs. This may be a digital plane, analog plane, maybe another USB or something. So if you got different planes, then we already discussed like something like this. What I discussed is the meaning is which we already discussed. Then when I show this one, it is clear. See, when you have digital analog part, better to have a tandem decoupling here, because then this will act as a local source for this one, so that your circuit is finished here, circuit is closing here. When you have digital, again tandem, so that circuit is closing here. So that's what this drawing says. So when you select decoupling capacitors, again there is an issue. You should have some, if the manufacturer is not providing you some values, maybe you have designed some digital circuit and then you found out some noise. Then what you do is you put the noise through the spectrum analyzer, and then you find out then some noise. Yeah, this is the frequency for the noise. Then you have to find out a capacitor. That capacitor got least impedance for that particular frequency. For example, your noise, when we analyzed the noise, the switching frequency is 3 megahertz. So your switching frequency is 3 megahertz. Then which capacitor you will select? Yeah, 2.2, because 2.2, that is the lowest impedance is 2.2. But then there is a question for you. For the capacitor, why we need this chart? Because from this chart we found out 2.2 got minimum impedance that is around 0.01 at 3 megahertz, and that is your region of interest. But then capacitive impedance equal to 1 by 2 pi Hc. When the frequency increases, what will happen to the impedance? It should decrease. So why then these curves are going up after some time? See, impedance is increasing. After this point, it is not coming down and shorting. See, if it is coming down and shorting, means then impedance will be 0. This is the impedance of the capacitor. This is the frequency. So why this is going up? So that is the problem. Your capacitor, this is an example of a parasitic inductor effect. So usually when the frequency is very high, after this 3 megahertz for 2.2 microfarad, the capacitor effect is less and inductor effect is taking role. So that inductor is the parasitic inductor that you don't see in the low frequency. So that's the reason we need this type plot for a particular capacitor. You can't put randomly some capacitor. So we have to look at this one and see, okay, because when especially high frequencies, the capacitor got a parasitic inductance, and then the parasitic inductance will take over at high frequencies. For the inductor, what happens is when the frequency increases for the inductor, the impedance will increase. So that's the reason, see, all the frequency. So that's the reason this curve, if you know this curve, at this point what is happening is your capacitance and inductance are cancelling out. So that's the reason here you are getting a minimum impedance point. So then we should know each capacitor what is this point, because we have to select that one for your IC. Obviously you can put another one, but then the effect is less. For 3 megahertz maybe I can use the green one, still it will short it, but then because impedance is this much, it will not short properly. So this is the best. So this is an example. You might be wondering what I am talking about, parasitic. So there is a parasitic capacitance, parasitic inductance, parasitic resistance. For example, each capacitor got a parasitic inductance, so the capacitor is not a capacitor at high frequency. So for example, the 2.2 microfarad, after 3 megahertz, it is an inductor, not a capacitor. So that is called a parasitic. It's not there, you made as a capacitor, but high frequencies, that effect coming into picture. It will happen with your copper track. When the signal frequency increases, that is the reason the impedance of the track is coming into picture, which you did not connect it. So that is the reason high frequency designs are difficult. Then choosing and using bypass capacitors. So sometimes even in the breadboard, people have noted when you put an appropriate bypass capacitor, so there is a lots of high frequency noise displaying the DC level. See, approximate 10 millivolt peak to peak. So this one where they have observed is in the supply line. Your supply line, they are getting, see, lots of noises. There are regular spikes in excess of 50 millivolt because of the switching. Any power supply perturbation will couple directly into the circuit and get into the output depending upon the power supply rejection ratio. So for the IC also they have power supply rejection ratio, because people know that this type noises can come into the IC. So that IC also they make some circuit inside so that the noises will not much go into the input side. So that is called a power supply rejection ratio. So when they make IC, they put in some circuit inside so that some noises coming into the IC through the power supply is not affected. So how much it is not affected is decided by power supply rejection ratio. So most of the ICs, they are immune to some of the noises. It will not go in and quickly affect your IC. But then even if you with that one, if you don't have decoupling, you will see something like this with the power supply rejection ratio. This IC got a power supply rejection ratio. But then when you put a proper bypass capacitor, your power supply line is clean. So this is an example of a real effect. Here you can see some spikes coming. So think about this one, you are connecting to another analog IC, and then you may get this amplified, your circuit will be a mess. A large electrolytic capacitor for decoupling, that is a 10 microfarad even to up to 100, we don't use 100, but 10 is mostly used. No more than 2 inch always from the chip. The purpose of this capacitor is to be a reservoir of charge to supply the instantaneous charge requirements of the circuits locally. So that's the reason that from that only your ICs are drawing the power, the switching power, and then circuit is closed there by that capacitor. So that the charge need not come through the inductance of the power trace. So it is not drawing far away regulator and then pulling through the track. Then a smaller cap as physically close to the power pins of the chip as is possible. A smaller capacitor, that is for bypass. The purpose of this capacitor is to short high frequency noise away from the chip. All decoupling capacitors should connect to a large area low impedance ground plane through via or short trace to minimize inductance. Optionally, small ferrite bead in series with power supply pin, which we already discussed, because when you have noise in one region, you have another noise in another region in the power supply, then you can put an inductor, because inductor short DC, but then it is inductor will the impedance of the inductor increases as the frequency increases. You know what I meant? So the inductor can isolate the noises, but then capacitor not, because capacitor is only bypass the noise. So you can think of capacitor is sensitive to voltage variation, inductor sensitive to current variation. So inductor doesn't like variation in the current, capacitor doesn't like variation in the voltage. So decoupling capacitors are present a low impedance at high frequency. AC supply currents are supplied by the decoupling capacitors instead of the supply, which we already discussed. This decoupling capacitor is your local source, and then circuit is closed there. So distribution strategies again, which we already discussed in the drawing. So this is your regulator, and then you will be putting a big tantalum capacitor. Then if you got analog part, maybe analog part, again digital part, and then or low frequency, different domains, different types of circuits, then you can have a ferrite bead for the power supply, because then this switching will not come to this part and then couple to your analog part. Maybe this is a digital part. That also we already discussed. Then this is another example. See, this is your power supply, and then the power supply, when the frequency increases, as I said, this track got inductance and resistor. Then if you got, this is your IC, digital IC, then if this is your power supply, then the power supply current is coming through all the way when this is switching on. When switching off, it is not coming, and then the circuit is closing like this. The current is coming and then coming through the ground and switching, and then when this is switching on and off, it is constantly drawing current, not drawing current. See, then a lot of noise is generated, and then it is also affecting your here because of the inductance and resistor, mainly inductance. There could be also some attenuation. But when you put a local capacitor, what is happening is here, that is your decoupling. Then now the decoupling capacitor, this is fully charged, and then this IC is drawing from the decoupling, and then it is see, circuit is closed here, and then this much effect you don't have it. So it is not drawing from the power supply, it is drawing the switching supply requirements from this capacitor, decoupling on. Even decoupling, this is another example with decoupling, without decoupling. So if you have something, power supply is coming, and then this is op amp, it will be going and then it coming out, then it is current is going through all the way back to here. Circuit is finishing because circuit should be closed. But if you got a decoupling capacitor here, what will happen is the op amp will be drawing current from this capacitor, and it is taking this output is coming and then closing here. See, such a short length. So the capacitor can minimize the length of the length to finish the circuit. So decoupling, this is some way of people have done for the USB. See, they have used a ferrite bead, then there is another capacitor around 100 nanofarad, there is a 10 microfarad, and then this is a USB ground. For RD0505D, see an example, and then this part, maybe you are getting a -5, then again you got some capacitor 10 microfarad, then 100 nanofarad, and then this you can connect your ICs, and then this +5 you can connect your ICs. Then somebody put LED here so that know that it's on in the power supply. So this is one way of doing. So you don't need this LED, but if you want, you can put an LED here so that when the power supply is on, then this LED is lighting, means you are definitely -5 is going. If this is maybe another color, so that +5 definitely is going, something like that. So this is an example, but here the example is, you can see this part is connecting to your IC. Then you can see here, see, this is your big capacitor tantalum. So this is your local source. It is not drawing from this one, it is locally drawing from here. Then capacitor impedance and series self resonance. So this we should be learning, capacitor impedance and series self resonance. So capacitors have a series self resonant frequency due to parasitic inductance. So which I have already shown you some curve where capacity impedance is increasing at high frequencies. So every capacitor capacitor has a self-resonant frequency. We call it a series self-resonant frequency due to parasitic inductance. So this is a high frequency model of a capacitor. So Low frequency one means this is only this capacitor. So high frequency one means you got the capacitor, then you got an inductor in parallel, then you got a small resistor, equivalent series resistance, then you also got a parallel resistor. See, so this is so C0, that is a nominal capacitance as a frequency defined by a manufacturer. So this is a high frequency representation of a capacitor, and then C0, that is the value manufacturer is talking about, 2.2 microfarad, means that is the value of this C0. Then at high frequencies we have to take into account this RP, this inductor, and then this resistor. Means you don't have to take into account, these things will come into picture. So your capacitor will look like something like this at high frequencies. So that is called high frequency representation. That is the reason in the previous circuit you have seen after a couple of megahertz the inductor is taking over. But in your DSO you will not see any of these effects. So that's the reason we are teaching you, except your ground you should be isolating. But then these type of responses you will see when you are designing high frequencies. Your DSO, you might think that it is high frequency, but it is not at all high frequency. 20 megahertz, people will laugh at you if you say high frequency. Because 20 megahertz is a big frequency for you, but 20 megahertz is not at all a big frequency, especially these days. As I told you 15 years ago, 2013, we designed 2.54 gigahertz using Rogers board. So even if you say 2.54, people would say that it was there in 2012. When I was a student, we designed 2.54 communication circuit, optical communication, 2.54. Still I remember the circuit. We have got the parallel lines, 155 megabits per second. We use a parallel to serial converter and make it 2.54 gigahertz, and then driving the laser diode. Then we got some communication on-off PPM. Then again in the receiver we are detecting using photodetector, then amplifier, transimpedance amplifier, then again serial to parallel conversion. So the whatever is coming into board is so many parallel lines, 155 megabits per second, and then we are serializing. So that's the reason 20 megahertz is not really a high frequency. Yeah. So coming back to the slide, so the capacitor got a series self-resonant frequency, and then the effective capacitance. Then people might ask, what is the effective capacitance? Because here the manufacturer says this is a capacitor, actually that is a low frequency value. So when you take into account all the parasitic components, then your new capacitance, because of these things, everything we have to take into account. The inductor we have to take into account. If you don't take into account this inductor, then what will happen is you don't get that response. It will be slowly decreasing. Your impedance of the capacitor is 1 by 2 pi fc. When the frequency increases, your impedance is decreasing and will become 0. It is not happening. After some time it is going up. So we have to explain why that is going up. So that is the reason we have to take into account all these parasitic components. So then effective capacitance equal to C0. That is a value at low frequency divided by 1 minus 2 pi F0 the whole square Ls into C0. So capacitor's series self-resonance frequency FSR is defined as 1 by 2 pi Ls into C0, means it got a series self-resonance. Then again when you have a resonance, then there is a Q factor. So sharpness of the resonance is expressed as Q equal to XC, impedance of the capacitor, minus impedance of the inductor, divided by effective resistance parallel RP. So these both are coming in parallel, and then impedances we minus out. So that is the Q value. So then why we are learning? Because that is the reason here, this point, when you have impedance of a capacitor, this is a tantalum, this is a ceramic, and then when you increase the frequency, it is decreasing. Normally it should decrease and become 0 when the frequency is infinity, but that's not happening. After some time it is going up. Again with the ceramic it is coming down and is going up. So this part is because of here capacitance is cancelling out with inductance. So this point. So that is a resonance. As at capacitor series self-resonant frequency, the reactance from C0. So the reactance of the capacitor and inductor are equal and opposite, yielding a net reactance of 0. So that is not actually 0, very low value. So this low point, This point is called the self-series resonant frequency of the capacitor. At this point, what is happening is your reactance of the capacitor is equal to reactance due to the inductor in the capacitor, parasitic, but then both are in the opposite direction, because capacitive reactance and inductive resonance are in the opposite direction, and then that is the reason you are getting this low value. This is due to the self-series resonant frequency. If you want to explain this effect, you need to take into account the high frequency capacitor model. Then this is a reactance. So reactance, what will happen? Reactance, see, this is a capacitive reactance. Capacitive reactance will decrease as the frequency increases. Inductive reactance will increase when the frequency increases. So for the capacitor, at some point, your low frequency capacitance, the frequency is decreasing, but the parasitic will be increasing as the frequency increases. At some point here, your XL minus XC both are equal and in opposite. So this point, this occur. This is reactance small. So that is the reason this is due to capacitor series. You please remember series self-resonant frequency. And then, so this is an example. So some data sheet will give you a designer can maximize rejection of an unwanted RF frequency, especially in RF we are dealing with high frequencies, by selecting capacitor with a series self-resonance frequency corresponding to unwanted frequency. Means so even some capacitor manufacturer will provide some curve like this, and then if you want to reject it, then you can reject, okay, to reject 1.9 gigahertz, then you may need maybe 15 pf. If you are using that particular capacitor, then this is a curve. Then if you got 1.9 gigahertz noise, then you can use 15 pf, means this manufacturing, if you are buying from this manufacturer. Then capacitor also got a parallel self-resonance. Series is there. What do you mean by parallel? So parallel self-resonance is created by you by mounting. So if you look at it, your capacitor, you can mount it, because capacitor means it's made of so many layers, like sandwiches, 2 layers sandwiched by a dielectric. So in sometimes what will happen is in your circuit, if you are mounting the planes in parallel, then what will happen is high frequency capacitor mode with the parallel capacitance. So if you are mounting like this, then parasitic parallel capacitance plate to plate. So you got a lot of parasitic plate to plate capacitance, then you will see like this, so many dips. When your frequency increases, what will happen is some places you get a resonance low reactance, another one you get another low reactance, so you will get something like this. Then if you put your capacitor properly like vertical, then you can avoid so many spikes. Still you are getting some, because you are getting so many layers, still it is forming some parasitic. So these are some things you might notice when you are designing high frequency, and then you can think of, oh, you should not mount it in parallel, if you know the layering, you can mount it vertical, and then you can avoid some of these type issues. Again, for the DSO, it's not really a problem, because you don't have anything like this high frequency. But then when do you use a PCB, which we already discussed? What is high frequency? A common guideline is that frequencies of a few hundred kilohertz and above have return currents which follow the path under the signal trace. The actual frequency above which we consider as high is determined by the trace board geometries. Yeah, so then there is another definition of high frequency. So when people talk about high frequency, there are people take into account another effect. So that a common guideline, which is some people frequencies of a few hundred kilohertz and above have the return currents which follow the path under the signal trace. So the meaning is, so you look at this circuit. So this is your power supply, maybe a capacitor here, power supply point, or a regulator here. So then that is coming to the IC output is going to this IC, then the return is coming and then going here. And then IC1 sourcing DC current, then IC1 sourcing the high frequency signal current. Then, so because this IC, you can see here, this is your power supply, regulator maybe. And then this is IC, and then this IC is drawing DC and the AC, the IC, because this IC got DC part and the AC part. And then what will happen is the DC current is coming from the power supply, then it is going here and then it is going here. So this is a DC. When it is AC, what will happen is then this capacitor is blocking the DC, this capacitor is blocking the DC. All the DC currents will be going like this, coming to this IC and returning. But all the AC currents, this path may be not low impedance. Your regulator, going through the regulator may be not low impedance. So then for the AC part, AC signal, switching circuits will be drawing current from this capacitor going to the IC, then it is coming here and then it is coming here. See, you know what I meant? So in your circuit, your IC will be taking DC current and AC current. When AC current is taken when you are connecting a signal. If you are not connecting a signal, it is DC, because then you are not switching on any of the transistors. Then when it is not switching on, then it will be taking your current from this VDD, and then that is your regulator, and then the current will be going to the IC and then it is coming. But when it starts switching at high frequencies, the high frequency current for that particular frequency, this path will be having more impedance. And then so this will be provided through the capacitors. This capacitor will be providing, and then that is going through. See, that is the reason IC sourcing high frequency signal current. So it will be like that, which we already discussed. Yeah. So another important is path of least resistance. Yeah. So this is a very important concept when you design high frequency PCBs. So maybe this is a place where most of the time, maybe I would say 60% time people make mistake because they don't know the path of least resistance and least impedance. So at lower frequencies, maybe in few kilohertz or DC, the current follows the path of the least resistance. Means, so this is a PCB and then this is a driving gate, driving IC, and then this is a track. So this is your copper track and then resistance, and then the dotted line is the ground plane. And then your signal is going through this copper track, and then the signal will come here, and then through the ground plane the signal should return. So when the signal is returning DC, low frequency, very low frequency, then it will follow the path of least resistance. So which is the path of least resistance? Just a shorter distance. So these are lost. But when it comes to AC signal, AC high frequency signals, it will follow not path of least resistance, least impedance. So then what will happen is at high frequencies, current flow follows the path of least inductance, means your current is flowing through this copper track, again the return is just below that one. You know what I meant? So the current is going in one direction, and then you got some curves, the return current will follow just under the track at high frequencies. Because at high frequencies, the return current on the ground plane is following the path of least impedance. So that is the reason when you make ground plane at high frequencies, you have to keep this in the mind. Your return signal will be like this. Maybe you will put a cut there, then it can't go, you know what I meant? So that is the reason you have to keep this in mind when you design. That is the reason auto routing might be not good. Auto routing for high frequencies might create issues. If you put auto routing, even your DSO, maybe it will mess up your ground planes. Please don't use auto routing. Maybe I will recommend auto routing when you have AI. After AI introduced, then it might take care of your design needs. But maybe during this time, once I used auto routing, but then it made a big mess. When you have digital and analog, it will mess up. Then you can use auto routing for maybe for some simple circuits, but then that is easy. You can route it. So one of the places auto routing will mess up is these high frequencies. Then path of least impedance. Again, as I said, the current flows in the path of least resistance. This is only true for DC currents. Current flows in the path of least impedance for AC signals. See, then when from this IC, this is a signal. So all the signal high frequencies come to this, and the return will be through this one. For DC, if you got some DC current, DC component, the return will go from here to here like this. The AC will be going like this. So return current interference. So that is the reason when you have making holes, you have to make sure that maybe you made these holes for the, here you don't have the copper. Maybe this one is you made for the components, but you have to make sure that your track is not on the other side, because the return path should go through it. Again here, see, this is the track, and if you put a cut like this in the ground plane, then your return path will take a round and then come here, because it's difficult to come under it. So that will create maybe some issue because of the return current. Inductance, your inductance will be more. And also when you have return current, as I said, in the ground plane, suppose you got so many ICs, returns are coming to the ground plane, then you have to make sure that because the ground plane is not static, the return means the current is flowing